Have you ever wondered, if the universe could speak, what would it tell us? It's true that sound cannot travel through a vacuum, but that doesn't mean there is only silence out there. On the contrary, the universe is a vast symphony where the vibrations of plasma, X rays, or gravitational waves are translated by scientists into sounds we can perceive. In today's video, you will hear the most mysterious and terrifying sounds from the farthest reaches of the universe. From the eerie wails of comets, the spine-chilling roars of supermassive black holes, to the echoes of black hole collisions that happened billions of years ago. Each sound not only makes us shiver, but also opens a door to a deeper understanding of the universe's secrets. Hit subscribe and stay until the end of the video, because you definitely won't want to miss a single sound in this mysterious journey. When it comes to the sounds of space, most people are surprised. How can there be sound in a vacuum? Indeed, in the absence of air, sound waves cannot propagate. But what few people know is that the universe actually resonates with countless kinds of oscillations, from plasma waves, radio waves, X-rays, to even gravitational waves. We cannot hear them directly, but thanks to the process of data sonification, scientists have converted these oscillations into sounds that the human ear can perceive. And that is the key to unlocking a world both eerie and magnificent, where every frequency, every echo carries within it the secrets of the universe's motion. Let us begin the journey of exploration with Saturn, the giant planet whose stunning rings have fascinated countless generations. Behind that spectacular beauty lies an extraordinarily strange symphony. Sounds coming from the collisions and twists of dust, ice, and plasma around its enormous magnetosphere. In 1997, NASA launched the Cassini probe, one of the greatest missions in the history of space exploration. Beyond taking pictures and analyzing the composition of the atmosphere, Cassini was also equipped with an ultra-sensitive system to record electromagnetic oscillations and plasma waves around the planet. As Cassini glided through the delicate yet dense rings, its instruments detected vibrations that seemed non-existent. Tiny dust particles, some only a few hundred nanometers across, about the size of a virus, struck the detector, creating tiny plasma bursts. The sounds converted from these oscillations are truly chilling, crackling, hissing, like the noise of an electronic storm in the dark. Even more frightening, during its final orbit in 2017, Cassini transmitted to Earth a special recording of plasma waves linking Saturn and its icy moon Enceladus. Just 2 weeks later, the legendary spacecraft dove into Saturn's atmosphere to end its 20-year mission. Imagine, that was the last voice Cassini left for humanity, like an acoustic testament of the universe. If the sounds of Saturn are enough to send shivers down your spine, Comet 67P Churyumov-Gerasimenko is even more mysterious. This was the first comet in human history that a spacecraft, the European Space Agency's Rosetta, successfully landed on. When Rosetta approached 67P in 2014, its plasma sensors detected unusual oscillations in the surrounding environment. When sonified, these data transformed into a ghostly sound so strange that many compared it to the voice of an alien creature. Interestingly, unlike comets observed before, the sound of 67P contained multiple layers: a steady clicking rhythm reflecting the cyclical changes in plasma density, a continuous buzzing representing the constant oscillations of the magnetic field as the solar wind blew through. To the ear, it resembles the eerie soundtrack of a science fiction film, both unfamiliar and stimulating to the imagination. But scientifically, this sound is extremely important. It provides researchers with detailed information on how the solar wind interacts with primordial matter from the birth of the solar system. In other words, when we listen to 67P, we are not only hearing the song of a flying ice rock, but also listening to the echoes of more than 4 billion years of cosmic history. The third sound in our journey takes us somewhere entirely different: the Perseus Galaxy Cluster, about 240 million light-years from Earth. Hidden deep at its center is a supermassive black hole, about 17 billion times the mass of the Sun. For decades, telescopes have detected X-rays coming from this region, caused by hot gas being pulled into the black hole's accretion disk. Yet it was data from NASA's Chandra X-ray Observatory that revealed a terrifying secret: the black hole was playing music. In 2003, Chandra recorded pressure waves spreading through the hot gas of the Perseus cluster, essentially sound waves. But because their wavelength was so long, humans could not hear them directly. Not until 2022, thanks to data sonification technology, did scientists speed up the frequency by trillions of times to bring it into the range of human hearing. The result? A heavy, guttural roar, like it came straight from hell, resonating in the listener's ears. Even more astonishing is that the original frequency of this sound was so low, it was considered the deepest note in the universe, 57 octaves below middle C. Far from being just a creepy experience, the music of the Perseus black hole carries profound scientific meaning. It suggests that sound waves emitted by the black hole may transfer energy into the surrounding environment, heating plasma across the entire galaxy cluster. This process may suppress or regulate the rate of star formation over time, directly influencing the evolution of an enormous galactic system. Once again, what we thought was only a bizarre sound turned out to be a vital clue about the dynamics of the cosmos. And finally, this sound journey leads us to a discovery considered one of the greatest scientific triumphs of the 21st century: gravitational waves. Predicted by Albert Einstein in 1916, gravitational waves are like ripples spreading across the surface of water when a stone is dropped. The difference is that instead of shaking a pond, they ripple the very fabric of space-time. For decades, they were thought to be undetectable, their amplitude far too small. Even Einstein himself doubted that humans would ever hear them. Yet starting in 2015, observatories such as LIGO, United States, Virgo, Europe, and KAGRA, Japan, proved otherwise. When two black holes collided and merged billions of years ago, they generated enormous ripples that spread throughout the universe. By the time these waves reached Earth, LIGO's ultra-sensitive lasers detected an incredibly tiny distortion, just a fraction of a thousandth the diameter of a proton. When this data was sonified, we heard a distinctive chirp, rising in frequency and then vanishing, like the final heartbeat of a pair of black holes before merging into one. That brief chirp, which at first seemed meaningless, actually changed forever the way humans see the universe. It confirmed one of the boldest predictions of general relativity and opened a new era of astronomy, gravitational wave astronomy. And every time we listen to that sound, we are not only hearing a scientific signal, but also the echo of an event that happened billions of years ago, a message transcending time sent to humankind today. The sounds from black hole collisions that we have just heard are only the beginning. In fact, the technology behind detecting gravitational waves is just as fascinating as the cosmic phenomena it reveals. Unlike optical or radio telescopes that you often hear about, these giant headphones have no lenses or mirrors. Instead, they operate based on one of the most precise instruments humans have ever built: lasers. In vacuum tunnels stretching for several kilometers, laser beams are emitted and reflected back and forth continuously. If nothing happens, these beams align perfectly. But when a gravitational wave from some distant place passes through, it causes spacetime to expand and contract in an unimaginably tiny way. To put it simply, imagine you are measuring a strand of hair, and suddenly it is stretched or compressed by just 1/10,000th of a proton's diameter. That is the level of sensitivity scientists are working with, a refinement almost beyond belief. And when this change occurs, the laser beam shifts slightly, creating a difference in frequency, like a guitar string vibrating at different pitches. It is thanks to this method that we can hear the voice of the universe. The low buzzing sounds usually reveal the slow collision of two moderately sized black holes. Meanwhile, fast, intense, sharp sounds come from the violent merger of supermassive black holes. Every time the data is converted into sound waves, it feels as if we are listening to a unique symphony composed by the universe itself. One of the most memorable recordings is the signal from two black holes colliding about 5 billion years ago. When that event was sonified, we heard a chirp, a short but powerful cry containing energy equivalent to 5 suns being converted into energy in an instant. Thinking about such grandeur, you can clearly feel that the universe is not silent, but resounding with ferocious symphonies beyond imagination. What is astonishing is that not only gigantic collisions create cosmic music. Even in near Earth space, electromagnetic oscillations have painted a strange symphony. Did you know that at about 60 kilometers above the ground, the human ear can no longer hear natural sound? That is because the air density is no longer sufficient for sound waves to propagate. However, in that region of space, countless other waves exist, especially radio waves and plasma waves, and when converted into sound, they reveal a vibrant world we never imagined. One of the most striking phenomena is the chorus waves in the Van Allen belts, the massive radiation zones surrounding the planet. Charged particles here are pulled back and forth by Earth's magnetic field, creating electromagnetic oscillations. When sonified, these waves sound like a mysterious choir, often occurring at dawn on Earth's sunlit side. That is where the name dawn chorus comes from. Listening to them, you feel as if an invisible orchestra is playing right above Earth's upper atmosphere. In particular, another type of plasma wave has an impressive name, Whistler waves. They form when lightning in the atmosphere discharges upward, then bounces multiple times within Earth's magnetic field. The result is a strange sound, starting at a high pitch, then sliding downward like a long whistle. Interestingly, this phenomenon is not just a natural curiosity, but also helps scientists study how lightning's energy propagates and affects the ionosphere. In a sense, every time a thunderstorm erupts, Earth is also singing its own melody. Farther out, the sounds in the magnetotail, the magnetic tail trailing behind Earth, also carry strange tones. Here, electrons are swept toward the planet's dark side, colliding with plasma and producing oscillations that sound like bird song in space. That clear, cheerful sound is evidence of the unceasing dynamism of the magnetosphere, where streams of particles and charges compose their own music. Meanwhile, another type of wave, called hiss waves, produces eerie, chilling hisses. They are thought to be echoes of chorus waves leaking outward, but when heard by the human ear, they evoke ghostly scenes, as if space itself were whispering a dark secret. If Earth and its magnetosphere have already given us a rich symphony, then the sun creates an even more colossal stage of music. Of course, in the ordinary physical sense, the sun is silent, since there is no medium for sound to travel through the vacuum between it and us. But when scientists collect pressure waves and particle oscillations from probes such as the Parker Solar Probe, then convert them into sound, we can hear the voice of our star. What surprises people is that the sun does not produce just a single sound. Each layer of its structure, from the photosphere, corona, to erupting plasma streams, has its own voice. Some recordings sound like a generator roaring endlessly. Others resemble the infinite ringing of a gigantic bell. And when you imagine that our Earth lies 152 million kilometers away from this star, yet its sounds resonate strongly enough to reach scientific instruments, you realize the immense power of nuclear fusion inside the sun. In just a single second, the sun produces an amount of energy equivalent to millions of times the world's total annual electricity output. If space could truly transmit sound waves as Earth's atmosphere does, then the sun's noise would be so deafening that life as we know it could hardly exist. But thanks to sonification technology, we can access that sound safely, like a window to listen to the heartbeat of the only star keeping life alive on Earth. The sounds of gravitational waves, plasma in the magnetosphere, thunder reverberations, and even the sun's songs all resonate into a grand symphony that humanity has only just begun to explore. The universe is not silent. It is simply speaking in a language the human ear cannot hear directly. Thanks to science, we have learned how to translate that language into sounds, both eerie and beautiful, so that every time we close our eyes and listen, we feel ourselves connected to the deep pulse of the cosmos. If the sun has given us a gigantic roaring symphony, where every stream of plasma and magnetic flare turns into super cosmic screams, then Saturn tells a very different story. If you listen closely, this planet is like a cosmic organ, where sound is no longer a burning chaos, but instead haunting, lingering echoes, as if resonating from an ancient cosmic play. The Cassini spacecraft, in its 15-year journey around Saturn, inadvertently became both a musician and a composer. Using its radio wave receiver and plasma instruments, Cassini translated invisible electromagnetic signals into something the human ear could perceive, a cold, eerie, yet mesmerizing symphony. Interestingly, these sounds did not come from any physical instrument at all. They were the product of colliding energetic particles swept into spiraling currents within Saturn's vast magnetosphere and its orbiting moons. When scientists first released these recordings, the public could not hide their astonishment. The sounds resembled whale calls echoing in the deep ocean, sometimes like a choir of trapped souls in space. For many, it was a spine chilling experience, but for astrophysicists, it was a treasure trove of information. Each pulse, each shifting frequency, was a key to decoding how Saturn's magnetosphere functions, how its radiation belts interact, and even how its tiny moons survive as they quietly orbit the giant planet. One of the most famous recordings came from Enceladus, Saturn's icy moon, which once erupted with plumes of water hundreds of kilometers high into space. When Cassini flew past, it not only observed vapor jetting from cracks in the ice, but also heard strange vibrations. Those signals, when sonified, produced a sequence of eerie whispers, as if coming from a hidden ocean beneath the ice. From these sounds, scientists strengthened the hypothesis that Enceladus may harbor a subsurface ocean where conditions for life could potentially exist. It's hard not to shiver at the thought. The sounds we hear might be the echoes of a world that could harbor life. They are no longer just dry data, but an emotional experience, as if the universe were whispering to us through each frequency. And Saturn doesn't stop there. When Cassini crossed the ring region, radio signals transformed into another harmony, crackling, buzzing, sometimes fast, sometimes slow, like the static of an old radio catching signals in the dead of night. These sounds revealed how ice particles collided, bounced, and maintained the miraculous stability of the ring system we admire from afar. Without them, Saturn's magnificent spectacle might only be a faint mist. This brings us to a bigger question. Perhaps the universe is not just a place to look at, but also to listen to. Imagine if we could build a cosmic sound library where every planet, every star, every black hole had its own symphony. Then science would not only be about measurements and formulas, but also an artistic journey where humanity resonates with the cosmos through sound. Returning to Cassini, its journey ended in 2017 when the spacecraft plunged into Saturn's atmosphere and burned like a shooting star. But what it left behind, terabytes of data and cosmic symphonies, continues to live on in our imagination. And perhaps that is the clearest proof that science is not only knowledge, but also the art of storytelling through the very sounds of the universe. In fact, this is the true power of sonification. It allows us not only to see, but also to hear the cosmos. A collision between two black holes may appear on a graph as complex mathematical curves, but when turned into sound, it becomes a chirp, a sharp, resonant pluck, like a vibrating string that quickly fades. In that fleeting moment, we feel the staggering scale of the universe more directly than any chart could convey. Saturn and the Sun are just two among countless instruments of the cosmos. Out there, quasars, supernova explosions, and colliding galaxies each create their own frequencies. What matters is whether we have the patience and technology to translate them into the language of the human ear. Because after all, the universe is not silent. It is only waiting for us to learn how to listen. And once you do, you will realize that every sound, whether the roar of a black hole or the whisper of an icy moon, carries within it a story, a secret, a message from afar. If Saturn once sent shivers down our spines with the eerie roar of its auroras and the tiny collisions within its rings, then the journey of Cassini and Huygens brought humanity an even more precious treasure: fragments of sound that turned a distant world into a place we could perceive with our very own senses. The first thing to emphasize is this: everything Cassini recorded was not just to please the ear. Every audio file contained profound scientific data. For example, when Cassini passed through the bow-shock region, where the solar winds slammed into Saturn's magnetosphere, the sudden change in radio waves allowed scientists to precisely determine the boundary of the planet's magnetic field. Without that data, we would not be able to draw the picture of how Saturn shields itself from harsh cosmic radiation. But perhaps the most fascinating part lies in the storms of sound. Imagine this. On Earth, a single lightning bolt is enough to shake the sky. So on Saturn, where lightning is 1,000 times stronger, how terrifying must that power be? Cassini recorded radio waves from those storms, and when sonified, they sounded like endless crackling explosions. Each burst was a colossal lightning bolt, flashing through the dense cloud layers enveloping the planet. Those sounds may not resemble any thunder we have ever heard, but they evoke a primal power and unbelievable vitality within that seemingly alien atmosphere. And then there were sounds that did not come from Saturn itself, but from its tiny moons. Enceladus, the icy gem, seemed to whisper through plasma. When Cassini flew by, it detected a plasma conduit linking Enceladus to Saturn, similar to the electromagnetic connection between Io and Jupiter. But unlike Io, Enceladus also spewed massive plumes of water from an underground ocean beneath its ice. The bending of plasma waves and magnetic fields revealed the presence of a thin atmosphere, sustained by these eruptions. The sounds Cassini captured there resembled the moaning of a trapped ocean, a melody so strange it inevitably raised the question, could life exist beneath that ice? But while Enceladus unsettled us with its mystery, Titan touched our emotions with its uncanny familiarity. In 2005, the Huygens probe separated from Cassini and descended into Titan's atmosphere, and this was one of the rare times we truly heard another world with a real microphone. As Huygens pierced the dense atmosphere, the microphone recorded the sound of rushing wind, oppressive silence broken by faint vibrations, exactly what human ears would hear if sitting on that probe. That moment nearly erased the distance of billions of kilometers. It made Titan no longer just a speck through a telescope, but a vivid world with its own sounds and rhythms. The sounds from Huygens became even more moving when we remember that Titan is the only place beyond Earth with rivers, lakes, and rain, but not of water, of liquid methane. That means when we hear Titan's wind blowing through the microphone, it may very well have swirled across the surface of a methane lake, creating a natural music unlike anywhere else in the solar system. Throughout the Cassini-Huygens mission, sound always played the role of an emotional lens. Every crackle, every moan, every gust of wind was not just data, but a reminder that the universe is not as silent as we once thought. It is always talking to us, through plasma, through magnetic fields, through dust collisions, and through distant winds. In fact, one of the most surprising discoveries came from Cassini's passages through the gap between Saturn and the D ring. At first, scientists thought there wasn't much dust there, but when reanalyzed with more sensitive instruments, they found countless tiny particles too small for the RPWS instrument to detect, visible only to the cosmic dust analyzer. Those particles, when colliding with Cassini, produced faint ticks like dust rain falling on the spacecraft's body. Those subtle sounds painted a new picture of a gap once thought to be silent. In reality, it was full of activity, simply beyond our initial detection. All of this proves a simple but profound truth. Science is not only about seeing, but also about listening. The sonification of data, turning radio waves and plasma into sound, not only helps the public approach the universe in a more intuitive way, but also helps researchers discover details that charts sometimes miss. A fleeting beep or crackle can open up an entire story about plasma, magnetic fields, or subsurface oceans. When Cassini ended its mission in 2017 with a heroic death in Saturn's atmosphere, it did not go in silence. The final data and sounds it sent back were its farewell, like the last echoes of a cosmic instrument finishing its symphony. For humanity, that legacy is not only scientific knowledge, but also proof that the universe can be experienced through every sense, even hearing. And perhaps that is the greatest value Cassini left behind. Thanks to it, we do not only know what Saturn looks like, but we have also heard it sing. The music of the cosmos never stops. We only need the patience to listen. As Bepi Colombo continues its 7-year journey, each flyby of a planet brings us new pieces of the mysterious scientific puzzle surrounding Mercury. From the very first images captured in 2021 to the most recent encounters, the spacecraft is not merely taking pictures or making measurements. It is revealing the stories that this small but harsh planet wants to tell. And within them, we find lessons not only about Mercury, but also about the very way the universe works. One of the discoveries that has most excited scientists is the data on Mercury's magnetic field. Previously, when NASA's Messenger spacecraft was active, we already knew that Mercury had an unusually weak magnetic field compared to its size. But why would such a small planet, with a core making up most of its mass, still maintain magnetic activity? With modern instruments, Bepi Colombo has helped clarify this puzzle. Mercury's magnetic field is not only weak but also asymmetric. Its north pole is stronger than its south pole, like an off-center magnet. This suggests that the planet's core may still be partially liquid rather than completely solid, and that asymmetry in its motion generates the strange magnetic field we observe. This is an important clue for understanding the thermal evolution inside Mercury, a planet lying right next to the Sun yet still retaining an active core. Alongside the magnetic field, Mercury's surface is also a treasure trove of data. From afar, it may remind you of the Moon, with countless craters scattered across it. But as Bepi Colombo draws closer, more striking details emerge. Gigantic impact craters, such as the Caloris Basin, are not only traces of a violent past, but also gateways that lead us back to the early days of the solar system. These craters were filled with lava billions of years ago, proving that Mercury once had intense volcanic activity. The tiny planet we often think of as geologically dead actually burst with energy in the distant past. And the fact that those lava plains still leave such clear marks today is evidence of Mercury's remarkable ability to preserve its history, as if time flows more slowly there than on Earth. Another fascinating discovery comes from the bright spots on Mercury's surface, known as faculae. These areas reflect unusually strong light, possibly originating from exotic minerals or mysterious outgassing from the crust. When Bepa Colombo flew past, its cameras recorded the brightness and morphology of these spots in detail. Scientists believe these bright patches may reveal clues about Mercury's unique chemical composition, completely different from the other rocky planets in the solar system. If Earth has water and carbon as the foundation for life, then Mercury may possess its own distinct chemical signature, reflecting the extreme conditions of its proximity to the Sun. Not only the surface, but Mercury's fragile atmosphere, or more accurately its exosphere, is also of particular interest to Bepi Colombo. This exosphere is extremely tenuous, almost a vacuum, but it contains particles of sodium, potassium, and even oxygen. How can these elements exist around such a scorching planet? Data show that the exosphere is maintained by continuous bombardment from the solar wind and micrometeoroids, which knock material off the surface and into space. In other words, Mercury's atmosphere is the result of a balancing act between erosion by the sun and the replenishment of material from the planet's own surface. Studying this mechanism not only helps us understand Mercury, but also gives us deeper insight into how planetary atmospheres form and evolve. What makes Bepi Colombo's journey so special lies not only in the data, but also in its complex trajectory. To reach Mercury, the spacecraft must perform multiple flybys of Earth, Venus, and Mercury itself, gradually slowing down. This is one of the most difficult missions humanity has ever designed, because instead of accelerating away from the sun, Bepi Colombo must continually brake to avoid being pulled too strongly by the sun's gravity. Each flyby not only conserves fuel, but also provides an opportunity to gather valuable scientific data. This winding journey has turned Bepi Colombo into a mobile laboratory, studying not only Mercury, but also Earth, Venus, and the interplanetary space environment. When Bepi Colombo eventually separates into two orbiters, the Mercury Planetary Orbiter and MIO, at the end of its journey, we will enter a new phase of exploration. MPO will focus on detailed mapping of Mercury's surface and internal structure, while MIO will study the magnetic field and its interactions with the solar wind. This combination is like having two eyes looking in the same direction but from different angles, creating a three-dimensional picture. Thanks to this, long-standing questions, from why Mercury has a magnetic field to why it contains so many unexpected volatile elements, may finally find answers. Every image, every piece of data sent back from hundreds of millions of kilometers away is not just information. It is a bridge between humanity and a distant world. They remind us that although Mercury lies close to the sun and is scorched by its heat, it still preserves secrets that could reshape our understanding of the origin and evolution of planets in the solar system. And Bepi Colombo's journey, with its wondrous detours and surprising discoveries, is proof of the persistence of science, patient, meticulous, but always rewarding. When InSight touched down on the red surface of Mars at the end of 2018, it opened an entirely new chapter in the exploration of this planet. Unlike the highly mobile rovers such as Curiosity or Perseverance, InSight was a silent listener. Its mission was not to roam in search of mineral deposits or capture majestic landscapes, but to listen to the heartbeat of Mars from within. True to its name, InSight, meaning deep vision, this spacecraft was designed to reveal unprecedented secrets about the internal structure and geological activity beneath the Martian surface. One of InSight's most important instruments was SEIS, the ultra-sensitive seismometer. Built in collaboration with the European Space Agency and especially French scientists, CS could detect the tiniest vibrations, even more delicate than the footsteps of an ant. Once placed on the surface, CIS was protected by a dome-shaped shield against heat and wind, allowing it to distinguish between howling winds above and seismic tremors from deep inside the planet. And then, after months of listening, it captured what humanity had long awaited: Marsquakes. The first quakes recorded by InSight were not as powerful as those on Earth, but they were invaluable evidence showing that Mars still had geological activity. Each tremor was like a natural X-ray, traveling through the crust, mantle, and core. By analyzing the speed and path of the seismic waves, scientists could reconstruct the internal map of Mars, something we had previously only guessed at. Preliminary results showed that Mars's core was larger than expected and might contain significant amounts of sulfur and other light elements, making it less dense than Earth's core. This was a crucial clue to understanding why Mars lost its global magnetic field billions of years ago, causing its atmosphere to erode and the planet to become as barren as it is today. In addition to SEIS, InSight also carried another special instrument called HPT, or the Mole. This was a bold design, a self-hammering probe meant to burrow up to 5 meters underground to measure the heat flow escaping from within Mars. Unfortunately, HP2 encountered major difficulties right from the first few meters. Instead of penetrating the ground as intended, it got stuck in soil that was too loose and lacked enough friction to allow deeper progress. Despite numerous attempts by engineers, from using the robotic arm to press down the soil to adjusting the digging angle, the mole ultimately stopped at a depth of about 40 centimeters. Yet even this failure yielded knowledge. It showed that Martian soil was not what we had imagined, but had unique mechanical properties, revealing how wind, ice, and time had reshaped the planet's surface. Furthermore, InSight was equipped with RISE, a highly precise instrument measuring Mars's orbital wobbles. By tracking radio signals as Mars orbited the Sun, RISE allowed scientists to infer the nature of the planet's core, whether it was completely solid or still partly liquid. Initial results indicated that Mars' core remained at least partially molten, enough to influence the planet's dynamic balance. This added another piece to the big puzzle: why Mars once had a magnetic field, why it vanished, and what consequences followed. But perhaps one of the most impressive moments InSight gave humanity was not a number, but the very first sounds from Mars. The spacecraft's microphones, combined with SEIS data, recreated the whistle of wind across its robotic arm and the tremors of the ground as Mars quivered. For many, hearing sounds from another world was both mysterious and moving, as if we were truly there, sensing the thin atmosphere and the solitude of the red planet. During nearly 4 years of operation, InSight recorded more than 1,000 Marsquakes of varying intensity. Notably, some were powerful enough for seismic waves to rebound from the far side of the planet, giving scientists their first global view of Mars's internal structure. These data are now being used to refine geological models while comparing Mars with Earth and the Moon. Thanks to this, we better understand how rocky planets form, cool, and evolve over time. However, no mission lasts forever. InSight's fate was always tied to its solar panels. Mars is a dusty planet, and over time, thick layers of dust gradually coated the panels, drastically reducing their ability to generate power. Without strong winds to clear them, InSight slowly weakened. By the end of 2022, the spacecraft fell silent forever, closing its mission after nearly 4 years of service. Even so, the legacy of InSight is immense. It transformed silence into scientific music, turned invisible tremors into vivid data, and gave us the first close look into the inner life of another planet. Thanks to it, Mars is no longer just a barren red surface in our imagination, but a world with a heartbeat, with breaths, with a complex history and its own story to tell. Can you imagine it? When we sonify these data, it is not just a visual or auditory game. It is the only way for humans to touch aspects of the universe that lie beyond the limits of our senses. The center of the Milky Way, with the supermassive black hole Sagittarius A, long known as the galaxy's invisible heart, can now resound like a mysterious symphony. Every ray of light, every cluster of hot gas, every dying red giant star, all are transformed into tones. For us, who can only look at the sky as tiny points of light, this is the first time we can actually hear the universe speak. And yet, that is only one piece of the puzzle. When scientists convert gravitational wave data into sound, we even have the chance to listen to colossal collisions that happened billions of years ago. A heavy thump, stretched out and then quickly fading, is the sonic signature of two black holes merging 5 billion light years away. Stop and think about that. This event happened before Earth had diverse life, yet thanks to gravitational waves, its echo still reaches us today. Turning gravitational waves into sound does not diminish their scientific value. On the contrary, it allows us to feel more vividly that the universe can not only be seen but also heard. These experiences open up a new approach to science. For blind astronomers, sonification is a direct bridge. A complex radio image, full of noise and dry data, can be turned into recognizable sequences of melody. Suddenly, they are not just listening to music, but in fact exploring galaxies in a way even sighted people have never experienced. This transforms space science into something that belongs to everyone, not just the privilege of a few. Of course, we must not forget that the universe is far from gentle. The music of planets, comets, or the solar corona often carries eerie, sometimes frightening tones. The sound from Earth's magnetosphere is almost indistinguishable from the electronic screeches of a horror movie. The echo from Comet 67P is like the whispers of ghostly wails reverberating from distant darkness. And when scientists convert X ray data from a black hole devouring matter into sound waves, the result is a roar so deep that the human ear cannot perceive it. Only after speeding it up thousands of times can we sense it. This proves that the universe is truly noisy. It is just that we lack the ears to hear it. What is valuable here is this: each sound carries scientific information. The oscillation frequency reveals the temperature and chemical composition of plasma. Variations in intensity tell us the energy of cosmic events. Even the way sound waves echo in the data reveals the structure of objects we cannot touch. Just as earthquakes on Earth help humans map the underground, so too do cosmic sounds provide us with an invisible map of deep space. You may be asking, why should we care? Isn't this just an artistic trick? The answer is that science is not only meant to be read in dry reports. Science must also spark imagination and emotion. When you hear the symphony of the galactic center, you are not just accessing data, you are touching the primal beauty that the universe holds. This does not overshadow science. On the contrary, it gives science the power to reach more hearts. And that is exactly why NASA, ESA, and many other research organizations continue to invest in sonification projects, turning data into a full sensory experience. Looking more broadly, these cosmic songs also compel us to reflect on our place in the universe. Earth is merely a tiny note in the vast symphony of the Milky Way. The winds on Mars, the roar of black holes, the echoes of comets, all merge into an eternal composition, one that humanity has only just begun to learn how to listen to. Perhaps in the future, with more sophisticated technology, we will be able to hear signals from even more distant phenomena: exploding supernovae, colliding neutron stars, or even the resonances of the early universe. Imagine one day scientists not only mapping the universe with images, but also creating a sound library that preserves everything the cosmos has ever sung. Future generations could step into a room, close their eyes, and journey across billions of light years simply by listening. In that moment, the universe would no longer be distant or invisible. It would become part of the human experience, something everyone could share. So when you hear these sounds, remember that they are not merely special effects in a video. They are authentic fragments of scientific data, shared under the principle of fair use to inspire, to make you look up at the sky and wonder, What other songs are waiting to be discovered out there? And if you want to keep listening, keep feeling, and keep exploring with us, don't forget to subscribe and stay with us until the end of this journey, because what we hear today is only the overture. Do you realize the special thing happening here? We are not just listening to music from space images. We are stepping into an entirely new scientific method, turning data into sensation. Each wavelength of light, from X rays, infrared, to visible light, once nothing more than dry numbers captured by telescopes, is now translated into musical notes. From there, an invisible picture of the universe becomes a symphony that humans can hear with their ears and feel with their hearts. Take a moment to pause. The composite image of the Milky Way's center you just heard is not only beautiful, it is proof of how the universe operates. X-rays show us where extremely hot plasma shines brightly, where violent energy is bent by immense gravity. Infrared redraws the network of cold dust where new stars are silently forming. Visible light makes clear the star clusters and gas clouds familiar to the human eye. When these three melodies are combined, they create a multi-layered cosmic symphony, just as an orchestra uses violins, drums, and brass to tell a story. The miracle is that when separated, we can see each wavelength has its own voice. X-rays sound like an echoing void, full of danger and mystery, where supermassive black holes reign. Infrared murmurs continuously like a deep, steady background track, evoking images of dust and cool gas. Meanwhile, visible light brings resonant tones, where young stars are born inside dense gas clouds. On their own, we get lost in each little story. But when combined, we finally see the complete picture, a universe that is dangerous, creative, and breathtakingly beautiful. And then sonification does not stop at the Milky Way. You just heard Cassiopeia A's supernova remnant, where a star exploded about 11,000 years ago. If we only look at the image, we see a multicolored nebula, like cosmic fireworks. But when translated into sound, Cassiopeia A resonates like a pulsating wave from center to edge, each rise and fall reminiscent of a giant heart that has stopped beating. It is both a sorrowful melody and a vivid testament to the cycle of stellar life: birth, burning bright, then exploding and scattering heavy elements throughout the universe. The pillars of creation in the Eagle Nebula take us to a completely different scene. Translating the image into sound, we hear sprawling passages, sometimes interrupted by lone ding tones of newborn stars. Those massive columns of dust, stretching light years long, are the cradles of future stars. With our eyes closed, the music not only describes the shape of the nebula, but also evokes the very process of the universe's gestation, where chaos and order weave together to give birth to new stars. What makes these experiences valuable is their power to connect us, tiny beings on an ordinary planet, with the vast scale of the universe. When you hear Cassiopeia A or the Pillars of Creation, you are hearing stories that took place thousands, even tens of thousands of years ago. Light waves traveled for millennia to reach Earth, and now, through sonification, you not only see but also feel the flow of cosmic time. From a scientific perspective, the value of sonification also lies in this: it helps us detect details the eye might overlook. A faint dot of light might blend into an image, but when translated into sound, it rings out like a sudden note in a symphony, immediately capturing attention. This is why many astronomers propose using sonification as a research tool alongside imagery. Let's not forget that, for the blind, this is a doorway to the universe. For the first time, they can hear the shapes of nebula, star clusters, or supernova remnants. Imagine a boy blind from birth, experiencing the Milky Way through sound for the first time. Isn't that one of the most beautiful examples of how science can change a life? Going further, sonification also touches the realm of art. Many musicians have drawn inspiration from cosmic data to compose, transforming science into melody and bringing the universe closer to the public than ever before. When astronomical data becomes music, it is both a research tool and a work of art. And here, science and art no longer have boundaries. Together, they bring us closer to the ultimate truth. The universe is both a vast laboratory and an endless symphony. Perhaps the greatest value of this entire experience is the reminder that the universe is not silent as we once thought. It is always murmuring, echoing, even roaring. We just need the tools to hear it. And once you've heard it, you will find it hard to look at the night sky the same way again. because every star, every gas cloud, every nebula does not just shine, but also resonates, as if whispering to humanity, I am still here and I have a story to tell.